Welcome to homework.
This is the answer to chapter 14, problem number 67 from the Smith Organic Chemistry textbook. And we're told that treatment of this alcohol that I've drawn here with TsOH acid affords two products, M and N, with molecular formula C6H12. We're given NMR spectra for these two molecules. We're asked to draw structures for them and then to propose a mechanism that explains their formation. And so right away, looking at this, we see that there's an alcohol in the starting material and no alcohol in the product. So this, it occurs to me, is probably a dehydration reaction, in which case we are going to have the formation of a double bond. And so these two molecules, M and N, probably differ only in the position of the double bond. And we're given a formula C6H12. So I think a good place to begin is to calculate a quick HDI. So it's going to look like this. Minus 12 there. All of that over 2. And that equals 1. So I think I'm right. I think there's one double bond in each of these molecules, and we're pretty much talking about just a difference of where that double bond is going to be. So then we can look at the NMR data and start to try to assign meaning to some of these signals. So we have for M here, these first three signals are going to be methyl groups. Then we have a multiplet at 2.0 with an integration of 2, and a triplet at 5.1 with an integration of 1. Okay, and so I'm going to say that this multiplet at 2.0 is going to be a methylene group. And then because it's so far downfield at 5.1 ppm, I think that this final signal is going to be from an alkene proton. So again, 5.1 ppm, pretty far downfield, and that is consistent with where we would expect alkene protons to show up. Okay, and so putting all of that information together, along with the fact that this is just a dehydration reaction, so we can start by drawing the backbone of the molecule, which we know from our starting material. So it's going to look like this, and then somewhere in here is a double bond. Okay, so let's look at splitting. So we have our first signal, a 1.0 ppm triplet that integrates to 3. So we have a methyl group that's being split by a methylene group. So what I'm saying is this first signal corresponds to this methyl group, and this signal for our CH2 is going to be splitting it. And so that has to be there, and it has to be intact, so to speak. It has to be a CH2 group. And so that to me means that in this molecule, our double bond is here. And I know that because this last signal for the alkene proton has to be coming from a single alkene proton right there on that carbon. And so that's the only way to get all of this NMR information to sort of make sense. Okay, and so then looking at N, again, I expect the only difference between M and N really to be placement of a double bond. So I'm going to go ahead and draw back in the backbone of the molecule here, the framework. And then again, start thinking about each of these pieces of NMR data. So this first signal, That's going to be a methyl group. Let's skip the second signal. The third signal is going to be a methyl group. Okay. And so what I'm seeing here is that there are only 2 methyl groups. So we have 2 methyl groups intact this time instead of 3. So that should tell us that this time the double bond has to be a terminal double bond because it's sort of getting rid of one of our methyl groups. So I'm going to go ahead and put the double bond here this time. And so in this case, we have this 1.8 ppm singlet, and it's a singlet. So I'm going to go ahead and say that it's right there. And then our other methyl group, which is split into a triplet, is going to be right there. Yeah, and I think that that makes sense. And then when we look at these others, what we see are 2 methylene groups here and here. And then this time we have a 4.8 ppm doublet that integrates to 2H. And this is going to be our alkene protons this time. This time we have 2 alkene protons, right? So this signal is going to be coming from the 2 protons that are on this terminal alkene. And then the other 2 methylene groups, and unfortunately, I only have 4 colors. So I'll do these 2 in green. So we have 2 methylene groups here and here. Yeah, and so the one that's definitely split into a triplet. So actually, let me go ahead, and again, I do apologize that I sort of have to reuse colors here. But so this methylene group that's split into a triplet is going to be corresponding to these 2 protons because they only have 2 neighbors, which is what splits them to a triplet. And then I did that in green. Okay, and so the other the signal at 1.4 ppm that is split into a multiplet is going to be from these 2 protons, and it's split into a multiplet because it's being split by the other methylene group to its left and by the methyl group to its right. Okay, and so that's M and N. But of course, there is a second part to this problem. So we're also asked, unfortunately, to draw a mechanism that accounts for the formation of these 2 molecules. So we are starting from here with the alcohol right here. Okay, and we are treating this with TsOH acid. So HOTS, let's do it like that. So the first step here is going to be the lone pair on this oxygen, one of the lone pairs, grabbing this hydrogen and becoming protonated. So we now have protonated alcohol there. So OH2. And of course, there is a positive charge on this oxygen now. It has 3 bonds. And so one of these bonds is going to break. The electrons will revert to the oxygen and it will leave as water. So now we have a situation where we have a carbocation. So carbocation is going to be right here. And let me go ahead and draw this hydrogen in here. And so we're actually going to get a rearrangement. So this is a 1,2 hydride shift. So it's going to look like that. You may also know it as a carbocation rearrangement. And so remember, a tertiary carbocation is going to be more stable than a secondary carbocation. And so this molecule will rearrange in order to make the more stable carbocation, which is the tertiary carbocation. So there it is, now with the positive charge housed on a tertiary carbon. Okay, and so basically one of 2 things can happen from here. And really they're the same thing. So we have a hydrogen here, or I guess I'll do this like this. We have the exact same molecule, but we can think about a hydrogen here. And so if the conjugate base of the TsOH acid that we started with plus this hydrogen, our new double bond will be terminal, and we will get the structure that was referred to as N on the previous page and in this problem. So this would be molecule N, or if the conjugate base of the TsOH acid takes this proton instead, oops, I should put that positive charge there, the new double bond will form not terminally, but in the interior of the molecule there. And so in that case, we would get the molecule that was referred to as molecule M in this problem on the previous page. So there we go. There's the mechanism that accounts for the fact that we get both of these molecules in combination when performing this reaction. So there's the stepwise mechanism that we were asked for. And then here again on this page are the structures of M and N and how we derived them by doing an HDI and then looking at NMR data. And that's the answer to chapter 14, problem number 67.